Out there in the vast cosmic ocean, beyond the familiar swirl of our own Milky Way, lies a galaxy that doesn't play by the rules. NGC 262 isn't just another speck of light in the night sky. It's a treasure chest of cosmic oddities, stuffed with objects so bizarre they make astronomers scratch their heads in wonder. Picture a place where the laws of physics seem to bend, where structures defy explanation, and where every new discovery feels like stumbling upon a secret the universe forgot to tell us. This isn't science fiction, it's real, it's happening, and today, we're diving deep into the heart of this galactic enigma to uncover 30 of its strangest inhabitants. What makes NGC 262 so special? For starters, it's a galaxy that refuses to fit neatly into any textbook category. While most galaxies behave predictably, spiraling gracefully, or sitting quietly as ellipticals, this one throws curveballs. Some of its objects glow with energies that shouldn't exist, while others vanish and reappear like cosmic ghosts. There are structures so massive they warp space itself, and phenomena so fleeting they're gone before we can fully understand them. It's as if the galaxy is teasing us, dangling clues to mysteries we're only beginning to grasp, and that's exactly why we're here. Over the next few minutes, we'll embark on a journey through NGC 262's most mind-bending wonders, from rogue black holes that wander like cosmic nomads to strange, pulsating bodies that might just rewrite what we know about star formation. Each of these 30 objects tells a story, and together they paint a portrait of a galaxy that's anything but ordinary, so buckle up. Whether you're a seasoned space enthusiast or just someone who loves a good mystery, this exploration promises to leave you with one burning question: how much stranger can the universe really get? The first strange object we encounter in NGC 262 is a sight that seems ripped straight from the mind of a cosmic artist, the Twisted Nebula. Unlike the delicate, wispy shapes we see in most nebulae, this one looks like someone took a handful of glowing gas and wrung it out like a wet towel. Its spiraling tendrils stretch across light years, curling inward and outward in ways that make physicists double-check their equations. Normally, gravity pulls matter into predictable shapes, spheres, disks, or gentle arcs, but here the rules seem to bend. The tendrils don't just spiral, they kink and loop in sharp angles, as if some unseen force is sculpting them against nature's will. What's even stranger is what this nebula is made of. Most nebulae glow thanks to the usual suspects: hydrogen, helium, and traces of heavier elements. But the Twisted Nebula's light signature shows an odd cocktail of rare molecules, including compounds we usually only see in the hearts of dying stars. Some astronomers think this could be the wreckage of a stellar collision, where two massive stars slammed together and scattered their guts across space in a chaotic whirl. Others argue it might be the work of a hidden black hole, its gravitational pull warping the surrounding gas like taffy. Then there's the question of its eerie glow. While most nebulae shine with soft pastels, blues from ionized oxygen, reds from hydrogen, this one flickers with an unstable, almost electric hue. Some parts pulse brighter and dimmer in minutes, a behavior so erratic it can't be explained by normal stellar winds or radiation. It's as if the nebula itself is alive, wrestling with forces we don't yet understand. And that's what makes it such a standout, even among NGC 262's other oddities. Most space mysteries eventually fit into some existing category: supernova remnants, protoplanetary disks, or the like. But the Twisted Nebula, it laughs at our labels. It could be something entirely new, a cosmic phenomenon we haven't even named yet, and that's just the first object on our list. Just when you thought NGC 262 couldn't get any stranger, along comes a star that plays the ultimate game of cosmic hide-and-seek. Meet the phantom star, a flickering enigma that appears without warning, shines brilliantly for days or even weeks, then vanishes as if it never existed. Astronomers have caught it blinking in and out of existence at least a dozen times over the past decade, with no predictable pattern or explanation. One moment it's there, glowing like any other star in the galaxy. The next, it's gone without a trace, leaving telescopes staring at empty space. So what could possibly cause a star to behave this way? One leading theory suggests it's locked in a deadly dance with a black hole. Picture this: a massive star orbits too close to an invisible predator, and every time it swings near, the black hole's gravity shreds layers of its outer material. The stolen gas heats up as it spirals into the abyss, creating a sudden, bright flare, only for the star to dim again once it retreats to a safer distance. It's like a cosmic lighthouse flashing on and off as it circles danger. But here's where things get weirder. The phantom star doesn't just dim, it disappears entirely from every wavelength of light, as if it's been switched off. Normal black hole interactions leave behind traces like X-ray signatures or distorted starlight. This star, nothing. It's as if it winks out of reality itself. Some researchers have even floated the idea of exotic physics at play, like a naturally occurring, cloaking effect from warped spacetime or a dense cloud of cosmic dust that somehow eclipses the star completely at random intervals. Then, of course, there's the wildcard theory. Could this be something artificial? Before you dismiss it as science fiction, consider the math. The star's disappearances don't match any known natural phenomenon, and the precision of its vanishing acts is uncanny. A handful of scientists, admittedly on the fringe, speculate that an advanced civilization might be manipulating stellar energy, harnessing the star's power, or even using it as a beacon. While there's zero concrete evidence, the sheer strangeness of the phantom star forces us to ask, in a galaxy full of mysteries, how do we know where nature ends and something else begins? Whatever the truth, this celestial ghost challenges everything we think we know about how stars live and die. Most stellar behavior follows rules: predictable life cycles, gradual changes. But the phantom star laughs at predictability. It's a reminder that the universe still holds puzzles we haven't even learned to solve yet. And if this is just the second object on our list, imagine what other surprises NGC 262 has in store. Hidden among the chaos of NGC 262's strangest objects lies a world that would make even the wealthiest diamond merchants gasp. A planet that isn't just covered in diamonds but is essentially one giant cosmic jewel. Meet the Diamond Planet, a celestial body so dense with crystallized carbon that it scatters starlight like a disco ball floating in the void. Unlike Earth, where diamonds are rare treasures buried deep underground, this planet's very crust, and likely its core, is a labyrinth of sparkling carbon structures, some the size of mountains. Imagine standing on its surface, where the ground beneath your feet isn't rock or ice but an endless expanse of fractured light, glittering under the glow of a nearby star. How does something so extravagant even form? Most planets emerge from the dusty leftovers of star formation, clumping together metals, silicates, and gases. But the Diamond Planet story begins with a stellar catastrophe. Picture a massive white dwarf, the shriveled corpse of a dead star, rich in carbon and oxygen. If such a star collides with another or gets too close to a black hole, the unimaginable pressure and heat can compress its carbon into a crystalline structure, effectively turning it into a diamond the size of a planet. Some scientists believe this might be the fate of certain white dwarfs, their cores crystallizing over billions of years until they harden into celestial gemstones. But here's the twist: this planet isn't just a lifeless chunk of bling. Recent observations suggest it might still cling to a whisper-thin atmosphere, mostly helium and hydrogen, swirling above its diamond surface. That raises a tantalizing question: could life exist here? At first glance, the idea seems absurd. Without water or organic compounds, how could anything survive? Yet extremophiles on Earth thrive in places we once thought uninhabitable, from boiling hydrothermal vents to acidic lakes. If life here existed at all, it would be unlike anything we know. Perhaps organisms that metabolize carbon directly, their bodies built from the same crystal structures as the planet beneath them. And then there's the light show. Because the planet's surface is so reflective, it doesn't just passively shine, it flashes. As it rotates, faceted planes of diamond catch the light of nearby stars, creating sudden, brilliant flares visible across the galaxy. Astronomers have even debated whether these flashes could be mistaken for artificial signals, a natural beacon so precise it mimics the pulse of a lighthouse. The Diamond Planet challenges our assumptions about what a world can be. It's not just a scientific curiosity, it's a reminder of the universe's boundless creativity. From colliding stars to potential alien chemistry, this glittering oddity proves that even the most extravagant sci-fi fantasies might be hiding in plain sight, waiting for us to look closer. And if diamonds aren't rare in NGC 262, what other treasures might this galaxy be hiding? Deep within the swirling arms of NGC 262, there's a patch of space that defies one of the universe's most fundamental forces, gravity itself. Welcome to the Gravity Anomaly, a region where the invisible hand that governs the cosmos seems to forget its own rules. Here, light doesn't just bend, it spirals, twists, and sometimes even doubles back on itself like light trapped in a hall of mirrors. Stars on the far side of this anomaly appear in places they shouldn't, their images smeared across the sky as if space itself has been crumpled like a piece of paper. What could possibly warp gravity to such extremes? One leading explanation points to an unimaginably dense knot of dark matter lurking at the anomaly's heart. Dark matter is already mysterious. It doesn't emit light or interact with normal matter, yet its gravitational pull shapes entire galaxies. But in this region, astronomers suspect there might be a concentration so thick, so tightly packed, that it warps spacetime like a bowling ball on a trampoline. If true, this would be one of the most extreme dark matter structures ever observed, a cosmic fossil from the galaxy's violent past. Yet there's another, even more mind-bending possibility, a tear in the fabric of spacetime. Some theoretical models suggest that under certain conditions, the universe's underlying structure can develop kinks or folds, like a wrinkled bedsheet. If such a wrinkle exists here, it could explain why light takes such bizarre paths through the anomaly, zigzagging where it should flow straight. It's a concept straight out of advanced physics, but the math checks out. Spacetime itself might be tangled in this region, creating a natural gravitational funhouse. And then there's the wild card, ancient black holes. Not the solitary giants we're familiar with, but a swarm of primordial black holes, relics from the universe's earliest moments. These tiny, dense objects could be clustered together like bees in a hive, their combined gravity twisting light in ways a single black hole never could. It's a fringe idea, but if proven, it would rewrite our understanding of how black holes form and how they shape their surroundings. What makes the gravity anomaly truly unsettling, though, is its unpredictability. Most cosmic phenomena follow patterns. Neutron stars pulse like clockwork, supernova fade predictably, but this region changes its behavior. Some days light bends gently, other times it fractures into multiple images without warning. It's as if the anomaly has moods, shifting between calm and chaos on a timescale that leaves astronomers baffled. That unpredictability raises a tantalizing question. Could this be more than just a natural phenomenon? While most scientists dismiss the idea, a handful speculate that advanced civilizations might manipulate gravity itself using technologies far beyond our comprehension to harness or even redirect this force. It's an extreme hypothesis, but in a galaxy as strange as NGC 262, can we really rule anything out? Whether it's dark matter, space-time wrinkles, or something even stranger, the gravity anomaly reminds us how much we still don't understand about the universe's basic rules. It's a cosmic rebellion against the orderly laws we take for granted, and a humbling glimpse into the frontiers of physics. And if gravity itself can misbehave here, what other surprises might this galaxy hold? Tucked between the stars of NGC 262, there's a patch of darkness that shouldn't be doing what it does. At first glance, the echoing void looks like nothing, just an unremarkable emptiness where no stars shine, no nebulae glow. But point a radio telescope at it and the silence shatters. This void sings. Every few hours, it emits bursts of radio waves that ricochet across the galaxy like echoes in a cave, repeating with eerie precision. The signals aren't random noise, they're structured, almost rhythmic, as if the emptiness itself has a voice. So what's hiding in the dark? One theory points to a stealth black hole, one so old and cold it stopped devouring matter, lurking unseen. But instead of pulling things in, it might be ringing like a bell. When stray gas or dust drifts too close, the black hole's gravity could stretch and compress it, creating vibrations that translate into those repeating radio pulses. It's a cosmic version of running a wet finger around the rim of a glass, making it hum. Except in this case, the glass is invisible and the tone echoes across light years. Then there's the wormhole hypothesis. Some physicists suggest the echoing void could be a portal, a tunnel through space-time so stable that energy leaks out in predictable waves. Wormholes are purely theoretical, but if they exist, NGC 262's void might be the closest thing we've found to evidence. The echoes could be traces of particles slipping through from another time or place, their arrival times distorted into those strange, repeating signals. It's a long shot, but in a galaxy this weird, even the wildest ideas deserve a second look. But here's the twist, the echoes aren't perfectly identical. Some pulses arrive slightly out of tune, as if whatever's making them is changing. That rules out simple mechanical explanations and opens the door to something far stranger. Could this be a natural transmitter, a celestial phenomenon that somehow encodes information in its signals? A handful of researchers have even floated the idea of an ancient alien artifact, a beacon left behind by a long-gone civilization. While there's zero proof, the sheer precision of the echoes forces us to wonder, if nature can create randomness so effortlessly, why would it also create patterns this deliberate? The echoing void doesn't just challenge our understanding of space, it taunts us. Most cosmic mysteries eventually surrender to observation, revealing their secrets over time. But this one, it's content to whisper just loud enough to keep us listening. Whether it's a black hole's death rattle, a wormhole's signature, or something beyond our current science, one thing's certain: NGC 262 has a way of turning empty space into the most fascinating puzzle of all. Imagine a star so precise it keeps time better than the most advanced atomic clocks on Earth. Now meet the Clockwork Pulsar, a cosmic timekeeper that ticks with unnerving perfection. Nestled in the heart of NGC 262, this spinning neutron star emits beams of radiation like a lighthouse in the dark, but with one baffling difference. Its pulses arrive with such mechanical regularity, they seem almost engineered. Every 1.337 seconds without fail, a burst of radio waves streaks across the galaxy, so precise you could set your watch by it. Even among pulsars known for their rhythmic flashes, this one stands out. Most gradually slow down over millennia, their rotations decaying like a wind-up toy losing steam. But the Clockwork Pulsar, its timing hasn't drifted a millisecond in decades. What could explain such flawless consistency? One camp of astronomers argues for an extreme version of nature's precision. Neutron stars, the densest objects in the universe after black holes, are already cosmic oddities. Their immense gravity crushes matter into a soup of neutrons, and their rapid spins generate powerful magnetic fields. Under just the right conditions, perhaps a perfectly symmetrical shape or an unusually stable magnetic field, a pulsar might achieve this level of stability. It's rare but not impossible. The universe, after all, loves outliers. Then there's the elephant in the room, the ghost of LGM-1. In 1967, astronomers discovered a pulsar so regular they briefly nicknamed it Little Green Men 1, joking that its signals might be alien transmissions. While it turned out to be natural, the Clockwork pulsar revives that tantalizing question: could something or someone be behind this? The odds are vanishingly slim, but the possibility lingers. Artificial origins would require technology far beyond our grasp, perhaps a Dyson sphere-like structure harnessing the star's energy, or a beacon deliberately engineered to mark a location. Most scientists dismiss this as fantasy, but in a galaxy as strange as NGC 262, even the wildest ideas deserve a side glance. Here's where it gets weirder. Recent observations suggest the pulses aren't just regular, they're too clean. Natural pulsars usually have minor hiccups, glitches where their spins speed up or slow down abruptly. The Clockwork pulsar shows none. It's as if some invisible hand keeps it perfectly balanced, correcting any stumbles before they happen. Some theorists propose an unseen companion, a black hole or dense planet whose gravity stabilizes the pulsar like a counterweight. Others wonder if we're seeing a new class of object altogether, a hyperstable pulsar born under freak conditions, like a star that collapsed with near-perfect symmetry. But the real mystery lies in the pulses themselves. Buried in their rhythm are faint, repeating patterns, not random, but not simple either. It's as if the pulsar is encoding information in its ticks, though what that could be remains anyone's guess. Could it be a natural phenomenon we've yet to understand, like cosmic interference? Or is it, as a handful of researchers quietly suggest, something more? The truth is, we don't have enough data to rule anything out. That's the thrill of the Clockwork pulsar. It's not just a scientific curiosity, it's a riddle wrapped in a paradox. On one hand, it challenges our understanding of how neutron stars behave. On the other, it dares us to imagine the unimaginable. Whether it's a quirk of physics or something far stranger, one thing's certain. In a galaxy that thrives on defying expectations, this celestial metronome might be the most tantalizing mystery of all. Amid the swirling chaos of NGC 262, there's a cosmic dance so delicate it defies logic: the living dust cloud. Picture a vast, shimmering swarm of particles, each grain no larger than a speck of sand, moving in eerie unison. They twist, ripple, and regroup like a school of fish avoiding a predator, their motions too coordinated to dismiss as random chance. Most cosmic dust behaves predictably, drifting lazily on stellar winds or clumping into asteroids, but this cloud pulses with a rhythm that feels almost alive. What could orchestrate such synchronized movement? One explanation points to magnetic fields. In space, charged particles can align along invisible lines of force, creating intricate patterns. But the living dust cloud's behavior goes beyond simple magnetism. Its particles don't just align, they react. When a nearby star flares, the cloud contracts in seconds as if bracing for impact. When radiation levels drop, it expands again like a lung inhaling. This isn't passive drifting, it's dynamic, almost intentional. Then there's the biological hypothesis. Some astrobiologists suggest the cloud might harbor extremophile microbes, organisms that evolved to survive in the void. On Earth, bacteria thrive in hostile environments, from acidic hot springs to the vacuum-exposed exteriors of the International Space Station. If life can cling to existence there, why not in a dust cloud? These hypothetical spaceborne microbes could coat individual particles, using them as rafts, and communicate through chemical signals to move collectively. It's a long shot, but the sheer precision of the cloud's movements keeps the idea alive. But here's the twist: the cloud learns. Over years of observation, astronomers noticed it adapting. When a gamma-ray burst disrupted its structure in 2012, the cloud initially scattered only to reorganize within hours into a tighter, more resilient formation. By the next burst, it didn't scatter at all. It rippled, dispersing the energy harmlessly through its layers. That's not just chemistry, it's borderline problem-solving. Natural systems don't typically remember past events, yet this one seems to. Skeptics argue for a simpler explanation: emergent complexity. Flocks of birds and schools of fish achieve synchronized motion without centralized control, following simple rules like stay close and match speed. Maybe the dust particles interact through static electricity or light pressure, creating a similar illusion of intelligence. But even this theory struggles to explain the cloud's adaptive behavior. Emergent systems react in the moment, they don't improve over time. The most provocative idea that we're witnessing something entirely new, a form of cosmic life unlike anything on Earth. Not carbon-based, not water-dependent, but a self-organizing system where dust and energy replace cells and DNA. Philosophers have long pondered whether life could exist beyond biology, and the living dust cloud might be the first hint that it can. Whether it's magnetic artistry, spacefaring microbes, or a shadow of life we don't yet understand, one thing's certain: this isn't just a cloud, it's a challenge to our definitions of life, our assumptions about intelligence, and our place in a universe that might be far stranger than we ever imagined. And in a galaxy already overflowing with mysteries, that's saying something. Of all the oddities in NGC 262, few are as deceptively simple or as baffling as the Mirror Comet. Unlike the dusty, pockmarked ice balls we're used to, this cosmic wanderer gleams like polished silver, its surface so reflective it bounces back starlight with almost perfect efficiency. Most comets are loose piles of ice and rock, shedding material as they near a star, but this one doesn't erode. It doesn't even grow a tail. Instead, it glides through space like a flawless pane of glass, untouched by solar winds or radiation. So what's shielding it? The answer might lie in its bizarre composition. Initial scans suggest the comet's surface isn't ice at all. It's layered with a metallic alloy, something akin to a natural version of the mirrors in telescopes. Forged in the heart of an ancient supernova, this material would have been blasted into space and frozen into the core of a forming comet. Over eons, collisions and cosmic weathering could have stripped away the outer layers, leaving only this ultra-smooth metallic shell exposed. It's a cosmic jackpot, a freak combination of chemistry and physics that created nature's own mirror. Yet the real mystery is its orbit. The Mirror Comet doesn't loop gracefully around stars like most comets. It zips through the galaxy on a path so straight it's almost artificial. Some researchers speculate it got flung here by a cataclysmic event, like a supernova's shockwave or a black hole's gravity well. Others wonder if it's an interstellar interloper born in another galaxy entirely. The lack of a tail suggests it never gets close enough to stars for their heat to affect it, which raises another question: how does it stay so pristine? Even in the cold of deep space, micrometeoroids should have pitted its surface by now. Then there's the light show. When the comet's angle aligns just right, it doesn't just reflect light, it focuses it. Telescopes have caught flashes of amplified starlight arcing from its surface, as if it's acting like a natural lens. These bursts are brief but intense, like cosmic camera flashes illuminating patches of the galaxy we'd normally overlook. If harnessed, this effect could theoretically turn the comet into a gigantic signaling device or a beacon. That possibility has led to some wild speculation. Could the Mirror Comet be more than a natural oddity? Its flawless surface, strange orbit, and light-bending properties check a lot of boxes for something engineered, though there's zero direct evidence. Most scientists dismiss the idea, but in a galaxy where dust clouds move like living things and stars vanish without warning, dismissing anything outright feels risky. Whether it's a 1 in a trillion fluke or something else entirely, this cosmic mirror forces us to rethink what a comet can be and how much stranger the universe might get. Black holes are supposed to be the silent predators of the cosmos, swallowing light, warping space, and lurking in the dark without a whisper. But deep in NGC 262, one defies the rules. Meet the screaming black hole, an anomaly that doesn't just consume matter. it sings, or rather, it vibrates with gravitational waves so intense, astronomers have translated them into actual sound. The result, a deep, resonant hum that echoes across the galaxy, like someone dragging a bow across the universe's largest cello. How does a black hole, an object famously incapable of emitting sound, produce anything audible? The secret lies in gravitational waves, ripples in space-time caused by cataclysmic events, like two black holes colliding or a star being torn apart. Normally, these waves are faint, detectable only by ultra-sensitive instruments like LIGO. But this black hole is different. It's engaged in a violent, ongoing feast, pulling matter from a companion star in a chaotic, lopsided orbit. As the star's gas spirals inward, it doesn't flow smoothly. It stutters, creating shockwaves that jolt the black hole's event horizon. Each jolt sends a gravitational wave reverberating outward, vibrating space-time itself at a frequency low enough to be transposed into sound humans can hear. And what a sound it is! When scientists shifted the waves into our hearing range, they expected noise, random rumbles, or static. Instead, they got something unnervingly melodic, a sustained, oscillating tone that rises and falls in pitch like a distant siren. It's not music, but it's not random either. The pattern suggests structure, as if the black hole's turbulence follows hidden rhythms. Some researchers compare it to the resonance of a wine glass tapped with a spoon, where the tone depends on the glass's shape and thickness. In this case, the glass is the black hole's event horizon, and the spoon is the dying star's erratic death throes. Why is this black hole so loud? Part of it boils down to scale. Most gravitational waves we detect come from brief events, black hole mergers that last seconds. This one's scream is continuous because its meal is ongoing. The companion star isn't just being devoured, it's being slowly devoured, stretched into a spiraling ribbon of gas that lashes the black hole's surface like a whip. Each lash generates a fresh wave, creating a near-constant drone. Add to that the black hole's spin, a frenzied rotation that twists spacetime around it, and you've got a cosmic feedback loop amplifying the vibrations into a signature howl. But here's the spine-tingling part. The pitch is changing. Over the past decade, the tone has crept higher, suggesting the black hole's spin is accelerating. That shouldn't happen unless it's consuming more matter than physics predicts possible. One theory posits an unseen third object, a smaller black hole or neutron star, orbiting the pair and sporadically dumping extra material into the mix. Another, more radical idea is that the black hole isn't just spinning faster, it's growing younger. Certain models of quantum gravity suggest black holes might emit energy in ways that reverse their entropy, effectively turning back their internal clocks. If true, this black hole's scream could be the sound of time itself unraveling. Whether it's a chaotic meal, a hidden accomplice, or a crack in known physics, the screaming black hole forces us to listen. Most of the universe's wonders are silent, playing out in wavelengths invisible to our senses. This one, it speaks, and in its voice we might just hear the echoes of laws we don't yet understand. Gas giants are known for their swirling tempests, roaring hurricanes that could swallow planets whole, churning for centuries without end. But in NGC 262, there's a storm that doesn't swirl at all. It shapes itself. The Hexagonal storm is a monstrous weather system stretching thousands of miles across a nameless gas giant. Its edges so geometrically precise they look laser-cut. Unlike the chaotic cyclones we see on Jupiter or Neptune, this one forms a perfect six-sided figure, its razor-straight sides defying every law that says nature abhors a corner. How does a storm, a phenomenon built on turbulence, hold such unnatural symmetry? The answer might lie in the planet's rotation. Saturn, our solar system's most famous hexagon host, spins so fast that its polar jet stream gets sheared into geometric stability, like honey drizzled onto a spinning plate. But this gas giant rotates slower, its winds less violent. That makes the hexagonal storm even more baffling. Some theorists suggest an unseen force, perhaps a dense ring of metallic hydrogen deep in the planet's atmosphere, acts like a mold, channeling the storm's chaos into rigid form. Others point to standing waves in the atmosphere, where colliding wind patterns resonate at angles that reinforce the hexagon's edges. Then there's the storm's eerie persistence. Most planetary weather shifts over time, even Saturn's hexagon flickers. This one hasn't changed in decades. Telescopes have watched it weather solar flares, meteor impacts, and the gravitational tug of nearby moons, yet its shape holds unyielding. It's as if the storm isn't just a temporary disturbance, but a permanent feature etched into the planet's atmosphere. And then there's the color. While Saturn's hexagon is a pale yellow, this storm glows an unnatural shade of indigo, darker at the edges and almost luminous at the center. Spectral analysis reveals chemicals we've never seen in a gas giant's upper atmosphere compounds that typically form only in extreme pressures, like those found near planetary cores. How they rose to the surface is anyone's guess, but their presence suggests the storm might be a window into the planet's depths, a geyser of deep atmosphere material punching through to the sky. The most unsettling detail, the hexagon moves, not with the planet's rotation but independently, drifting across latitudes like a sliding puzzle piece. Storms don't do that, they're trapped by wind currents and planetary spin. Yet this one wanders as if guided by some invisible hand. Some researchers whisper about artificial megastructures, hypothetical planet-sized constructs that manipulate weather, while others insist it's just a freak of fluid dynamics we haven't cracked yet. Whether it's a natural masterpiece or something else entirely, the hexagonal storm forces us to rethink what's possible in an atmosphere. It's a reminder that even the most familiar cosmic phenomena can hide secrets, and that in a galaxy like NGC 262, even the weather refuses to follow the rules. In the vast expanse of NGC 262, there's a sight that seems to defy time itself: the frozen lightning. Stretching across light years, these jagged, branching structures glow with an eerie blue-white light, their razor-sharp tendrils arrested mid-motion as if someone hit pause on a cosmic explosion. Unlike the fleeting bolts we see on Earth, which vanish in milliseconds, these filaments hang suspended in space, unchanging for decades. It's as if the universe snapped a photograph of a lightning strike and forgot to put it away. So how does lightning, a phenomenon defined by its speed and chaos, freeze in place? The answer might lie in the plasma's bizarre state. On Earth, lightning is a rapid discharge of electricity, heating the air into a fleeting plasma. But in the depths of space, where temperatures and pressures defy terrestrial logic, plasma can behave in ways that seem almost supernatural. Some scientists suggest these structures formed during an extreme event, perhaps a collision between two neutron stars or a supernova's shockwave where energy surged through a dense cloud of ionized gas. Under those conditions, the plasma might have cooled so abruptly that its charged particles locked into place, preserving the lightning's shape like bugs trapped in amber. The real puzzle, though, is the structure's stability. Plasma is unruly by nature, its particles repelling each other with enough force to dissipate even the strongest formations. Yet these filaments hold their shape against all odds, their edges crisp as shattered glass. One theory points to an unseen magnetic field, woven through the lightning like an invisible scaffold, holding the charged particles in perfect tension. Another idea involves quantum effects, conditions so extreme that the plasma's particles became sticky, resisting the usual forces that would tear them apart. Then there's the question of what triggered the lightning in the first place. The frozen lightning doesn't connect to any obvious power source, no nearby stars, no swirling accretion disks. Some astronomers speculate it's the remnants of a failed black hole, a singularity that flickered into existence just long enough to unleash this energy before vanishing. Others wonder if it's evidence of a cosmic-scale electrical discharge, the kind predicted by fringe theories where galaxies are linked by vast currents we can't yet detect. But the most haunting possibility, that we're not looking at a snapshot of an event but at the event itself still unfolding. Time operates differently under extreme gravity, and if these filaments exist near a black hole or some other space-time anomaly, what we perceive as frozen might actually be a lightning bolt stretching across centuries from our perspective. It's a cosmic illusion, a trick of relativity that makes the instantaneous appear eternal. Whether it's a magnetic fossil, a quantum fluke, or a glimpse into warped time, the frozen lightning forces us to rethink what we know about energy and motion. In a universe where even the most fleeting phenomena can leave permanent scars, sometimes the most astonishing discoveries aren't about what's moving, but what refuses to. Somewhere in the silent depths of NGC 262, a ring of light glows where no light should be. The ghostly ring encircles a gas giant twice the size of Jupiter, its pale luminescence flickering like a candle behind frosted glass. But here's the catch: there's no star nearby to illuminate it, no reflected sunlight or stellar flares to explain its eerie glow. It's as if the ring generates its own light, a cosmic neon sign advertising mysteries we're only beginning to decipher. What could possibly power such a phenomenon? One leading theory points to radioactive decay on an unimaginable scale. Imagine countless particles within the ring, each carrying traces of exotic isotopes forged in the hearts of long-dead stars. As these atoms break down, they release energy in the form of light, a slow, steady shine that could explain the ring's persistent glow. On Earth, we see hints of this in radioluminescent materials like radium dials on old watches, but in NGC 262, the effect is magnified across billions of tons of dust and ice. Yet there's a problem with this explanation. Radioactive decay tends to follow predictable patterns, its brightness fading over time. The ghostly ring doesn't fade. It pulses, brightening and dimming in cycles that don't match any known radioactive timeline. That inconsistency has led some astronomers to propose an even wilder possibility: dark matter annihilation. If dark matter particles, those elusive, invisible building blocks of the universe, collide within the ring's dense structure, they could theoretically annihilate each other, converting their mass into pure energy. The resulting gamma rays might then interact with the ring's material, creating the soft glow we observe. It's a stretch, but in a galaxy already brimming with anomalies, could dark matter be the culprit? Then there's the ring's structure. Unlike Saturn's tidy bands, this one is frayed at the edges, its particles arranged in intricate, lace-like patterns. Close-up scans reveal gaps and clusters that suggest gravitational resonances, places where the pull of unseen moons or planetary waves might sculpt the ring's shape. But no moons have been found. Instead, the ring's delicate filaments seem to move independently, as if guided by invisible hands. Some researchers speculate these could be knots in spacetime itself, regions where microscopic black holes or quantum fluctuations twist the fabric of reality, bending light and matter into those ghostly braids. And then there's the color. Most planetary rings reflect the hues of their components: icy whites, dusty browns. The ghostly ring emits a cool, uniform blue tinged with occasional violet streaks. That spectrum doesn't match any known natural light source, leading a handful of fringe theorists to propose something truly radical: engineered luminescence. Could this ring be an artifact, its glow the remnant of some long-lost technology designed to harness or transmit energy? The idea sounds like science fiction, but in a universe where pulsars mimic metronomes and dust clouds move with purpose, dismissing it outright feels premature. Whether it's radioactive dust, dark matter fireworks, or something beyond our current science, the ghostly ring refuses to fit neatly into any box. It's a paradox, a structure both fragile and enduring, mysterious yet luminous. And in a galaxy where the impossible seems to lurk around every corner, perhaps the most unsettling truth is this: some lights shine not to guide us, but to remind us how much darkness still lies beyond our understanding. Amid the chaos of NGC 262's cosmic wonders, there's a small, unassuming rock that refuses to stay silent. The singing asteroid, a modest chunk of metal and stone no larger than a city, hums a tune across the void, a steady, harmonic vibration that resonates through the surrounding space like a tuning fork struck by the universe itself. Most asteroids are inert, tumbling quietly through the darkness, but this one pulses with rhythmic precision, emitting frequencies so clean they could be mistaken for music. What makes a space rock sing? The answer could lie in its composition. Early scans reveal an unusually high concentration of metals, not just iron and nickel, but dense alloys like osmium and iridium, materials often forged in the hearts of dying stars. These metals don't just sit there, they vibrate. When micrometeoroids strike the asteroid's surface, the impact sends shockwaves through its rigid metallic core, causing it to ring like a bell. But here's the twist: the vibrations aren't random. They cluster around specific harmonic frequencies, creating a chorus of overlapping tones that sustain far longer than physics predicts. On Earth, a struck bell sound fades in seconds. This asteroid's song lingers for hours. Then there's the shape. Unlike the lumpy, potato-like forms of most asteroids, the singing asteroid is eerily symmetrical, almost spherical, with smooth, polished patches that reflect starlight like mirrors. That symmetry might explain the purity of its tones. Just as a perfectly crafted wine glass produces a clearer ring than a cracked one, this asteroid's uniform structure could amplify and refine its vibrations. But how did it get so smooth? Collisions in space tend to leave surfaces pocked and jagged, not buffed to a shine. Some researchers speculate it was sandblasted by a nearby star's intense stellar winds, while others wonder if tidal forces from a passing black hole sculpted it over millennia. The real mystery, though, is the tune itself. The asteroid's vibrations aren't just harmonic, they're mathematical. When translated into sound, they align with the frequencies of the cosmic microwave background, the faint afterglow of the Big Bang. It's as if the rock is echoing the universe's oldest song. Coincidence, possibly, but the odds of natural resonance matching primordial radiation so precisely are astronomically low. That's led a handful of scientists to propose something radical. The asteroid might be engineered, not by aliens necessarily, but by some long-lost cosmic event that imprinted order onto chaos. Picture a supernova's shockwave compressing metal into a perfect resonator, or a neutron star's magnetic field aligning the asteroid's atomic structure like a cosmic blacksmith. Yet even those theories struggle to explain the most baffling feature: the asteroid's responsiveness. During a solar flare in 2019, telescopes caught its vibrations shifting, not randomly, but transposing into a higher key, as if adjusting to the new energy input. Natural objects don't adapt like that. Crystals resonate at fixed frequencies, metals dampen under stress. This asteroid, it changed its tune. That behavior has fueled wilder speculation, from self-tuning alien artifacts to fragments of a shattered Dyson sphere still carrying out their programmed functions. Most astronomers dismiss these ideas, but in a galaxy where dust clouds move with purpose and black holes scream in perfect pitch, the line between natural and artificial starts to blur. Whether it's a metallic relic singing the universe's oldest lullaby or something far stranger, the singing asteroid reminds us that even the smallest objects can hold the loudest secrets. In NGC 262, where anomalies pile upon anomalies, sometimes the most profound mysteries come not from the grandest structures, but from the quietest hums in the dark. Among the bizarre residents of NGC 262, few have caused as much confusion as the vanishing moon, a celestial body that plays an impossible game of peek-a-boo with astronomers. One week it's there, orbiting its parent planet like any ordinary moon. The next, it's gone without a trace, leaving telescopes staring at empty space. Then, just as suddenly, it reappears as if it never left. This isn't just a trick of the light or a glitch in the data. the moon genuinely vanishes from every wavelength, from radio waves to X-rays, defying every law we know about how objects in space behave. So how does a moon simply disappear? One theory points to an ultra-dense dust cloud, a shroud of microscopic particles so thick it swallows light whole. Most cosmic dust is sparse, scattering sunlight in delicate veils, but this hypothetical cloud would need to be more like a celestial blackout curtain. Picture a swirling mass of metallic debris, each particle coated in something akin to interstellar soot, absorbing radiation instead of reflecting it. If the moon's orbit carries it through such a cloud periodically, the effect would be like flipping a switch, one moment visible, the next erased. Yet even this explanation has holes. Dust clouds don't vanish cleanly. They leave traces, infrared glows, or subtle distortions in starlight. The vanishing moon leaves nothing. It's not just hidden, it's invisible, as if someone turned off its very existence. That's led some researchers to consider even wilder possibilities, like naturally occurring cloaking effects. On Earth, scientists have experimented with metamaterials, engineered surfaces that bend light around objects, rendering them unseen. Could nature have stumbled upon a similar trick? Certain exotic crystals forged in the hearts of neutron stars might theoretically warp light in ways that camouflage anything behind them. If the moon passed through a field of these crystals, it could effectively disappear from view. Then there's the timing. The moon doesn't vanish randomly. It follows a rough schedule, disappearing for days or weeks before reappearing. That kind of regularity suggests an orbital mechanic, perhaps an elliptical path that swings it behind some unseen structure, like a ring of dark matter or a warped pocket of spacetime. But no such structure has been detected, leaving this idea floating in the realm of speculation. And then, of course, there's the elephant in the room: artificial intervention. While most astronomers dismiss the idea outright, the precision of the moon's disappearances raises eyebrows. Natural phenomena tend to be messy. This is anything but. Could some ancient, advanced civilization have built cloaking technology into the moon itself? It's a stretch, but in a galaxy where pulsars keep perfect time and dust clouds move with eerie intelligence, ruling anything out feels premature. Whether it's cosmic camouflage, a dust cloud denser than physics should allow, or something even stranger, the vanishing moon forces us to confront a humbling truth. The universe is still full of tricks we haven't even begun to understand. And in NGC 262, the line between natural wonder and outright magic is thinner than we'd like to admit. On a rogue planet drifting through the emptiness of NGC 262, where no star warms its surface, there's a sight that defies logic, a river of fire cascading down a cliff face like a waterfall made of nightmare. The lava waterfall isn't just a trick of the light or a fleeting volcanic event. It's a permanent, roaring torrent of molten rock, glowing white-hot as it plunges thousands of feet into a basin of searing magma below. On Earth, volcanoes cool and harden when their heat source fades, but here, in the eternal dark of interstellar space, the lava never stops flowing. How does molten rock stay molten without a star's energy? The answer lies beneath the planet's crust. Most rogue planets freeze over time, their internal heat bleeding into space. But this world is different. Its core is a churning reactor of radioactive elements, isotopes so unstable they generate immense heat through constant decay. Picture uranium and thorium in concentrations far beyond anything in our solar system, their atoms splitting in a slow, natural fission process that turns the planet's interior into a self-sustaining furnace. The lava waterfall is just a vent, a crack in the planet's armor where that heat escapes, like steam whistling from a pressure cooker. But the real mystery isn't just the heat, it's the waterfall's impossible stability. Lava, even superheated, should cool as it spills into open air, forming a crust or splintering into brittle rock. Yet this cascade flows as smoothly as water, its surface shimmering with convective currents that suggest something stranger at work. Spectral analysis reveals traces of exotic metals, titanium, vanadium, even hints of metallic hydrogen dissolved in the lava like ingredients in a cosmic brew. These elements lower the magma's viscosity, allowing it to remain fluid at temperatures that should turn it sluggish. It's not just lava, it's a superconducting slurry, a cocktail of materials forged in conditions we've never replicated. Then there's the cliff itself. Most lava falls on Earth are short-lived, collapsing as their channels erode. This one carves through a mountain of obsidian-like rock, blacker than the void around it, yet somehow resisting the lava's fury. The secret might lie in its composition. Scans suggest the cliff is laced with carbon nanotubes, microscopic structures stronger than diamond, woven into the stone like reinforcement bars in concrete. How they formed naturally is anyone's guess. Perhaps the planet's extreme pressures and temperatures catalyzed their creation, turning ordinary carbon into a lattice tougher than anything we've ever seen. The most haunting detail, the waterfall pulses. Every few hours the flow surges as if the planet itself is breathing. Some researchers think this rhythm matches the core's decay cycles, where pockets of radioactive material reach critical mass and ignite like subterranean stars. Others wonder if tidal forces from an unseen companion, a neutron star or black hole, squeeze the planet's interior like a stress ball, pushing fresh magma to the surface with each gravitational tug. Whether it's a radioactive heartbeat, a hidden puppeteer, or something beyond our physics, the lava waterfall stands as a paradox, a beacon of heat in the freezing dark, a structure both violent and eternal. It's a reminder that even in the coldest corners of the cosmos, fire finds a way. And if molten rock can defy the void, what else in NGC 262 is waiting to shatter our expectations? The galaxy's strangest structures aren't always the ones that glow. Between the brilliant stars and swirling nebulae of NGC 262 stretches something far more subtle, a network of faint filaments crisscrossing the darkness like threads in a cosmic spiderweb. The cosmic web isn't just dust or gas. These tendrils connect stars and planets across vast distances, forming invisible highways through the void. Most galaxies have loose traces of such filaments, but here they're dense, organized, almost purposeful. So what holds this web together? The leading theory points to dark matter, that elusive substance making up most of the universe's mass. Dark matter's gravity could sculpt these filaments into a scaffold, channeling ordinary matter along its ropes like beads on a string. But there's a problem. The web's geometry is too precise. Natural dark matter structures tend to be clumpy and uneven, while this one forms near-perfect angles, intersecting at nodes where stars and black holes cluster like knots in a net. It's as if something or someone tied the galaxy together with meticulous care. Then there's the web's eerie effect on light. When distant starlight passes through these filaments, it doesn't just bend, it splits, casting multiple distorted images of the same star across the sky. This isn't normal gravitational lensing. It's more like light hitting a prism, except instead of glass, space itself seems fractured. Some astrophysicists speculate the filaments contain exotic matter, particles with negative mass or other bizarre properties that twist spacetime in ways we've never observed. Others wonder if the web is a fossilized relic from the galaxy's birth, a snapshot of primordial forces frozen in time. But the real mystery lies in the web's motion. These filaments aren't static, they ripple, vibrating in sync with distant cosmic events like supernova or black hole mergers. It's as though the entire structure is tuned like a violin string, resonating with the galaxy's heartbeat. That kind of coordination shouldn't be possible across light years unless the web isn't just a structure, but a system, transmitting energy or information through channels we can't yet comprehend. Could this be nature's version of a neural network, a vast interconnected web shaping the galaxy's evolution? Or is it something even stranger, a shadow of higher dimensions, where threads we perceive as filaments are actually the frayed edges of realities brushing against our own? In NGC 262, where the impossible feels routine, the cosmic web might just be the ultimate reminder. Sometimes the universe's boldest mysteries aren't in the stars, but in the spaces between. Deep in the swirling tapestry of NGC 262, one gas giant refuses to play by the rules. It doesn't just reflect light, it creates it. The bioluminescent gas giant shimmers like a cosmic disco ball, its atmosphere pulsing with radiant patterns that shift and swirl in hypnotic waves. These aren't the auroras we see on Jupiter or Saturn, fueled by solar winds. This planet's glow comes from within, as if its very clouds are alive with light. What could power such a spectacle? The leading theory points to chemiluminescence, chemical reactions in the upper atmosphere producing light without heat. On Earth, we see hints of this in fireflies or glowing plankton, where molecules like luciferin release energy as visible light. But on this planet, the scale is unimaginable. Picture vast storms churning up phosphorescent compounds from the depths, where pressures and temperatures forge exotic molecules we've never encountered. Some researchers speculate the glow comes from allotropes of oxygen or nitrogen, rearranged by the planet's extreme conditions into forms that sparkle like cosmic glitter. Yet there's a problem: the patterns. Chemiluminescence should be chaotic, flickering randomly as clouds collide. Instead, the bioluminescent giant's light moves with eerie coordination. Swirls expand in fractal spirals, pulses travel across latitudes like synchronized fireflies. That kind of order suggests something more than chemistry, perhaps biological processes. Could the planet's upper atmosphere harbor floating life forms, vast microbial mats that glow to communicate or harness energy? On Earth, entire ecosystems thrive in hostile environments, from acid lakes to radioactive waste. Why not in the dense, turbulent skies of a gas giant? The colors only deepen the mystery. Most atmospheric glows skew blue or green, the result of specific molecular excitations. This planet's palette includes hues we don't even have names for: shimmering golds, deep violets, and a fleeting shade some astronomers call void crimson, visible only in certain infrared bands. These anomalies hint at elements or compounds beyond our periodic table, or maybe quantum effects we've yet to understand. Then there's the rhythm. The planet's light show follows cycles unrelated to its rotation or any nearby stellar activity. Every 42 hours, the glow intensifies in a global wave, as if the entire atmosphere is breathing. Some theorists link this to tidal forces from an unseen moon, squeezing the planet's interior like a stress ball and releasing charged particles into the sky. Others propose a more radical idea: the planet might be conscious, not in the human sense, but as a self-regulating system where atmospheric currents and chemical networks interact in ways that border on emergent intelligence. It's a stretch, but in a galaxy where dust clouds mimic living systems, can we rule it out? Whether it's a chemical masterpiece, a floating biosphere, or something beyond our current science, the bioluminescent gas giant does more than dazzle, it challenges. It forces us to rethink where life could thrive, how chemistry can dance, and what it means for a planet to not just exist but to perform. And in NGC 262, where every corner holds a new enigma, this radiant world reminds us, sometimes the universe's most profound questions come dressed in light. Among the countless stars burning in NGC 262, one stands apart not by how it shines, but by how slowly it fades. The time-dilated star is a cosmic paradox, a celestial body that appears to be stuck in its own personal slow-motion universe. While neighboring stars burst into supernova or cool into husks, this one lingers in its prime, aging at a pace that defies every stellar model we have. According to its spectral lines, it should be a middle-aged giant, yet observations spanning decades show almost no change in its brightness or composition. It's as if time itself is bending around it, granting it an unnaturally long life. Einstein's theory of relativity offers a clue. Near massive objects like black holes, gravity warps spacetime so severely that time slows down, an effect called gravitational time dilation. For an astronaut orbiting close to a black hole, hours might pass while years slip by on Earth. The same principle could explain this star's sluggish aging, but with a twist: the distortion isn't caused by an external force. The star itself seems to be generating the effect, its core so dense that it twists spacetime into a knot around it. Spectroscopic scans reveal traces of exotic matter in its atmosphere, particles that might amplify gravitational fields beyond what normal physics predicts. If true, this star isn't just experiencing time dilation, it's manufacturing it, yet the mystery deepens. Most time dilation occurs in extreme environments, black holes, neutron stars, where matter is crushed into oblivion. This star, though massive, isn't compact enough to explain the effect through known physics. Some researchers speculate it's hiding a secret at its heart, a microscopic black hole no larger than a city, captured during the star's formation and now orbiting within its core. The black hole's gravity would tug on the surrounding plasma, creating a time-slowing bubble without consuming the star outright. Others propose a more radical idea, that the star is wrapped in a time crystal, a theoretical quantum structure that repeats in time instead of space, locking it in a near-perpetual loop. What really unsettles astronomers, though, is the star's influence on its surroundings. Nearby celestial bodies show subtle but measurable delays in their orbits, as if they're moving through syrup. Light from background stars stretches as it passes the time-dilated star's gravitational field, reddening more than standard models allow. Even more bizarre, certain elements in its corona appear frozen mid-decay isotopes that should have transformed into other elements millennia ago, still clinging to existence, as though radioactive decay itself has been throttled. Could this star be a natural time capsule preserving a snapshot of an earlier cosmic era? Or is it a fluke, a one-in-a-trillion alignment of physics that lets us glimpse how malleable time truly is? Whatever the answer, the time-dilated star forces us to confront a humbling possibility. In NGC 262, even the most fundamental constant, the tick of the universe's clock, might be up for negotiation. And if time itself can stutter here, what else in this galaxy bends the rules we thought were written in stone? Floating silently in the depths of NGC 262, the magnetic monolith cuts an imposing figure against the starry backdrop, a sleek, obsidian slab stretching nearly 12 miles from end to end, its surface so unnaturally smooth it reflects distant galaxies like a dark mirror. Unlike the jagged asteroids or gnarled comets we're used to, this structure has no craters, no weathering, no signs of cosmic wear. It just is as if carved by something or someone with impossible precision. But what really sets it apart isn't its appearance, it's the monstrous magnetic field that surrounds it, strong enough to warp the paths of nearby stars and snatch cosmic rays from light years away, bending them into swirling auroras that dance across its edges. At first glance, the monolith evokes the stuff of science fiction, a dead ringer for the enigmatic slabs from 2001, A Space Odyssey. Yet this isn't a cinematic prop, it's a real, measurable anomaly. Probes sent within 1,000 miles of it report instruments going haywire, their compasses spinning wildly as if caught in a cosmic whirlpool. The field isn't just powerful, it's structured, pulsing in geometric waves that ripple outward in perfect hexagonal patterns, like a beehive's hum translated into magnetism. Most natural magnetic sources, neutron stars, magnetars emit chaotic, lashing fields. This one behaves more like a tuned antenna, broadcasting on frequencies we're only beginning to detect. So what could forge such an object? One theory points to a freak stellar event, the hypernova of a magnetar, a neutron star with an already extreme magnetic field. Under just the right conditions, the explosion might have compressed and crystallized the star's magnetic energy into a physical form, like lightning frozen into a monument. Another idea involves exotic matter, particles with magnetic charges so strong they clump together into solid structures, creating a permanent magnet the size of a mountain range. Either scenario would require physics at the bleeding edge of what we consider possible, but in NGC 262, the impossible seems to be a starting point. Then there's the question of purpose. Natural formations don't usually do anything, they just exist, yet the monolith's magnetic pulses aren't random. They repeat in sequences that some mathematicians argue resemble prime numbers, a pattern often considered a potential hallmark of artificial design. Could this be a beacon, a navigational marker left by some ancient civilization to guide travelers through the galaxy? Or perhaps a cosmic battery storing magnetic energy harvested from stellar winds? Skeptics dismiss these ideas as wishful thinking, but the monolith's very existence already defies easy explanation. In a universe where black holes sing and dust clouds move with eerie intelligence, why should this be any different? The most unsettling detail, though, is its stability. Magnetic fields decay over time, their energy dissipating into space, yet the monolith's field hasn't weakened since its discovery decades ago. It's as if the structure is tapping into some unseen power source, maintaining itself against entropy's relentless pull. That defiance of cosmic decay raises a chilling possibility. Whatever created the monolith might still be maintaining it. Whether it's a natural phenomenon we've yet to understand or something far stranger, one thing's clear: NGC 262 has a way of turning even the simplest black slab into a riddle that echoes across the ages. And sometimes the most profound mysteries aren't just about what we see, but what lingers silent and unyielding in the spaces between. Of all the cosmic fireworks in NGC 262, none blur the line between reality and theory quite like the quantum quasar. At first glance, it behaves like any other quasar, a brilliant beacon powered by a supermassive black hole devouring matter at a frantic pace. But peer closer and contradictions emerge. Its light doesn't just flicker, it fractures, splitting into multiple spectra that suggest the quasar exists in several states at once. One moment, it's a young, voracious monster, its energy output spiking as if it's just begun its feast. The next, it's an aging relic, its glow dimming as though billions of years have passed. These shifts aren't gradual. They're instantaneous, as if the quasar is flipping between alternate versions of itself, a cosmic Schrödinger's cat, simultaneously alive and dead on a galactic scale. The strangest part, the quasar's behavior changes depending on who's watching. When observed with radio telescopes, its emissions suggest a stable, predictable structure. Switch to X-ray instruments and the data becomes chaotic, as if the quasar knows it's being scrutinized and alters its output accordingly. It's a staggering parallel to the observer effect in quantum mechanics, where the act of measurement changes the state of a particle. Only here, it's playing out across light years with an entire quasar as the subject. How could something so massive exhibit quantum behavior? One theory points to the black hole at its core. Under certain conditions, a black hole's event horizon might act like a quantum boundary, its immense gravity creating a zone where particles, and perhaps even larger structures, exist in superpositions. If true, the quasar's light could be a macroscopic echo of this quantum weirdness, its photons entangled across states we're only glimpsing in fragments. Then there's the space-time wrinkle hypothesis. Some models suggest the quasar sits at a knot in the fabric of the universe, where multiple timelines or dimensions briefly intersect. Think of it as a cosmic traffic jam, with realities piling up at a single point. The quasar's shifting states might be glimpses of alternate versions of itself, each occupying a slightly different universe but momentarily visible in ours. But the most unsettling possibility, that we're seeing the limits of causality itself. In quantum physics, cause and effect can blur. Events don't always follow linear order. The quantum quasar might be a rare case where this principle scales up, its changes untethered from time as we understand it. One observation captures it forming, the next shows it dying, with no middle ground in between. Whether it's a quantum fluke, a dimensional crossroads, or a challenge to physics itself, this quasar does more than shine, it questions. And in a galaxy where the rules seem written in pencil, that might be the most profound mystery of all. Imagine a world where the ground beneath your feet isn't rock or ice, but an endless expanse of glittering crystal, a moon so pristine it acts like a cosmic jewel dangling in the void. The crystal moon of NGC 262 is exactly that, a solitary satellite forged entirely from translucent minerals, its surface fractured into sweeping plains of jagged quartz, towering spires of beryl, and valleys of gemstones so pure they bend light like prisms. Unlike the dusty, crater-pocked moons we're familiar with, this one gleams with an almost unnatural clarity, its facets catching starlight and splintering it into rainbows that dance across nearby planets like celestial spotlights. How does an entire moon become crystalline? The answer lies in a perfect storm of cosmic conditions. Most moons form from the debris of planetary collisions, their materials a chaotic mix of metals and silicates. But this one likely began as a wandering asteroid, rich in rare minerals like corundum and topaz that drifted too close to its parent planet's gravitational pull. Over eons, tidal forces squeezed the asteroid like a stress ball, generating immense internal heat. That heat, combined with the moon's unusually pure composition, allowed its minerals to grow into vast, uninterrupted crystal lattices, some spanning hundreds of miles. Think of it as nature's version of a gemstone forge, where pressure and time transformed a lump of cosmic ore into a masterpiece. Yet the real magic happens when the moon aligns just right with its star. Because its surface is riddled with natural facets and fractures, it doesn't just reflect light, it manipulates it. Telescopes have observed distant stars appearing to warp or multiply near the moon's horizon, their images duplicated as if seen through a hall of mirrors. On rare occasions, when the angles align, the moon even projects intricate patterns onto nearby gas giants, geometric constellations that flicker briefly before dissolving. Early astronomers mistook these for alien signals, but the truth is even stranger. The moon's crystal planes act like a natural lens array, bending and focusing starlight with precision that rivals human-made optics. What's baffling, though, is the moon's durability. Crystal structures, no matter how large, should be brittle, prone to shattering under meteor impacts or thermal stress. Yet this moon's surface shows almost no scarring. Some researchers speculate its crystals might be laced with microscopic diamond fibers, a natural reinforcement akin to steel rods in concrete. Others propose the moon is geologically active in an entirely new way, with shifting crystal plates that heal fractures by fusing back together under pressure. Could there be practical uses for such a world? Theoretical physicists have floated the idea of the crystal moon as a cosmic observatory, a natural telescope where its refractive properties could magnify distant galaxies without distortion. Visionaries even dream of harvesting its minerals to build starlight-powered engines or quantum computing arrays. But the moon might already be serving a purpose we don't yet grasp. Some of its light-bending effects are too precise to be random, creating fleeting images that resemble symbol circles within circles, spirals, even what look like mathematical constants etched in light. Are these mere coincidences, or is the moon, in its own silent way, communicating? In a galaxy where the impossible feels routine, the crystal moon stands apart. It's not just an oddity, it's a testament to nature's capacity for artistry, a world where geology and optics collide to create something almost too beautiful to be real. And as its rainbows flicker across the dark, one thing becomes clear. In NGC 262, even the rocks refuse to be ordinary. Tucked away in the spiraling arms of NGC 262 lies a patch of darkness so absolute it doesn't just lack light, it consumes it. The stealth galaxy isn't a void or a shadow. It's a region of space that swallows every photon, every radio wave, every shred of electromagnetic radiation that dares to cross its boundary. Point a telescope at it and you'll see nothing, not the faint glow of distant stars, not the microwave whisper of the Big Bang's afterglow, not even the telltale heat signature of cosmic dust. It's as if someone cut a hole in the universe and stitched the edges closed. So what could lurk in this lightless abyss? One possibility is a dark galaxy, a ghostly sibling to our Milky Way, made almost entirely of dark matter. Most galaxies are anchored by vast halos of this invisible substance, their gravity sculpting the visible stars and gas into familiar spirals or ellipses. But a dark galaxy would take this to the extreme. No stars, no nebulae, just an island of pure, concentrated dark matter drifting through the cosmos. If the stealth galaxy fits this description, its gravitational pull might be the only clue to its existence, subtly bending the paths of nearby stars like an unseen hand tugging at the fabric of space. Yet there's a problem with this theory. Dark matter, while invisible, doesn't absorb light, it simply lets it pass through unhindered. For the stealth galaxy to blot out radiation so completely, it would need something else, a shroud of ultradense particles, something akin to cosmic soot, capable of trapping energy entirely. Some theorists point to primordial black holes, tiny, ancient singularities left over from the Big Bang, clustered so densely they form a light-swallowing net. Others propose a more exotic idea, a naturally occurring perfect absorber, a structure where quantum effects and gravity conspire to cancel out electromagnetic waves entirely, like a black hole's event horizon stretched across an entire region of space. Then there's the eerie silence. Most cosmic structures hum with subtle vibrations, gravitational waves from colliding neutron stars, the faint radio chatter of pulsars. The stealth galaxy emits nothing. Even the ambient noise of the universe seems to hush near its edges, as if sound itself is being sucked into the void. That silence has led a handful of researchers to speculate about artificial origins. Could this be a Dyson sphere scaled up to galactic proportions, a megastructure designed to harvest energy on an unimaginable scale, or perhaps a cosmic stealth mode, engineered to hide something from prying eyes? The odds are vanishingly slim, but in a galaxy where dust clouds move with purpose and black holes sing in perfect pitch, ruling anything out feels premature. Whether it's a dark galaxy, a quantum anomaly, or something beyond our current science, the stealth galaxy forces a humbling realization. Even in an era of advanced telescopes and deep space probes, the cosmos still holds pockets of perfect mystery. Some shadows aren't meant to be illuminated, they're reminders that for all we've learned, the universe keeps its deepest secrets close, waiting for us to ask the right questions. Amid the cosmic chaos of NGC 262, where most nebulae sprawl in chaotic splendor, the fractal nebula stands apart, not for its size or color, but for its eerie precision. This swirling cloud of gas and dust doesn't just drift, it repeats, its structure echoing the same intricate geometric patterns at every scale. Zoom in, and you'll see spirals within spirals, branching tendrils that mirror the nebula's overarching shape with uncanny symmetry. It's as if nature stumbled upon a cosmic stamp, pressing the same design into existence over and over again. How does something so orderly emerge from the randomness of space? One explanation lies in turbulence. On Earth, we see hints of this in river deltas or lightning strikes, where chaotic forces accidentally create fractal-like branches. In the nebula's case, shockwaves from nearby supernova or the gravitational pull of hidden black holes might have sculpted its gas into repeating waves, like ripples frozen mid-spread. Certain chemical reactions in the nebula's plasma could also amplify these patterns, with molecules aligning along magnetic fields to form crystalline-like structures on a galactic scale. But there's a catch. The fractal nebula's patterns aren't just similar across scales, they're mathematically identical. Natural fractals like coastlines or fern leaves exhibit rough self-similarity with variations creeping in at smaller levels. This nebula's ratios are precise, its angles crisp as if drawn by a cosmic compass. That level of perfection pushes the limits of known physics, leaving some researchers to wonder if we're missing a piece of the puzzle. Could quantum effects operating across light years lock the nebula's structure into harmony, or does it hint at something far stranger, a natural universe that inherently prefers order when conditions align just right? Then there's the elephant in the room, design. While most scientists bristle at invoking intentionality, the nebula's precision has sparked fringe debates. Its patterns resonate with sacred geometry, the same ratios found in ancient temples or Dine helices. Could it be a fluke, a one-in-a-trillion accident? Or is it a whisper of something deeper, a universal language written into the fabric of reality? Skeptics argue that human brains are wired to see patterns even where none exist. But in a galaxy where black holes sing and dust clouds move with purpose, the line between coincidence and clue feels thinner than ever. Perhaps the most tantalizing clue lies in the nebula's light. Certain wavelengths reveal subtle vibrations frequencies that match the resonant tones of plasma crystals in labs. It's as if the nebula isn't just a static sculpture, but a vibrating membrane humming a note we're only beginning to hear. Whether it's a cosmic accident, a quantum masterpiece, or something beyond our current science, the fractal nebula does more than dazzle, it challenges. It asks us to rethink how chaos becomes order, and whether the universe's blueprints might be more intricate than we ever imagined. Most black holes anchor galaxies like lighthouses, tethered to their surroundings by gravity's unbreakable chains. But drifting through the depths of NGC 262 is a rebel, the rogue singularity, a black hole untethered from any star or system, wandering the cosmos like a hungry ghost. Unlike its stationary cousins, which feast on steady streams of gas and stars, this nomadic predator relies on chance encounters, swallowing anything unlucky enough to cross its path. How does a black hole break free? The answer lies in cosmic violence. When two galaxies collide, their central supermassive black holes often spiral toward each other, locked in a gravitational dance. If a third black hole intrudes, the chaotic interplay can fling one of them outward at unimaginable speeds, a slingshot effect so powerful it overcomes the galaxy's pull. That's likely the rogue singularity's origin story. A three-way black hole brawl that ended with this one ejected into the void, carrying the energy of 1,000 supernovae in its wake. The dangers of such a wanderer are as vast as they are invisible. Without the glowing accretion disks that betray most black holes, this one drifts undetected until it's too late. Stars near its path don't explode or flare, they simply vanish, their light winking out as they're pulled past the event horizon. Entire planetary systems could be disrupted, their orbits warped into chaos long before the black hole's presence is known. Even light years away, its gravitational tide might stir comets from their icy nests, sending deadly showers toward inner planets, but the real terror lies in its unpredictability. Most cosmic threat supernova gamma-ray bursts follow observable patterns. The rogue singularity obeys no rules. It could barrel through a star-forming region tomorrow, snuffing out newborn suns, or lurk in the darkness for millennia, a phantom waiting to pounce. Some models suggest there could be hundreds more like it in NGC 262 alone, a swarm of invisible predators rewriting the galaxy's fate one silent encounter at a time. Yet this rogue isn't just a destroyer, it's a time capsule. Unlike black holes fed by constant streams of matter, its isolation means it's nearly pristine, preserving the conditions of its violent birth. Studying its faint gravitational ripples might reveal secrets about galaxy collisions, dark matter, or even the nature of space-time itself. If we could track its path, it could become the ultimate cosmic roadmap, its trajectory tracing the galaxy's most ancient cataclysms. Whether it's a bringer of chaos or an accidental historian, the rogue singularity defies the quiet order we expect from the universe. It's a reminder that even the darkest corners of space are alive with motion, and that sometimes the most terrifying things aren't what we see but what we don't. Far from the warmth of any star, a lone planet drifts through the icy void of NGC 262, its night side alive with a luminous spectacle that puts Earth's polar lights to shame. The Aurora planet doesn't just display the occasional ribbon of color. Its entire surface writhes under a perpetual storm of light, as if someone drenched the world in liquid rainbows and set them ablaze. Veils of emerald and violet twist like living things, while crimson tendrils lash across mountain ranges taller than Everest, casting their jagged shadows onto glowing plains below. This isn't a fleeting light show. It's a planet drowning in its own radiance, where the sky never darkens and the ground shimmers with reflected hues. What could power such an unending storm? The answer might lie in the planet's heart. Most planetary auroras, like Earth's, are sparked by solar winds, charged particles streaming from a star, guided by magnetic fields to the poles. But this rogue world has no star. Instead, scans reveal a core of pure, swirling magneto-hydrodynamic chaos. Imagine a dynamo the size of a moon, churning molten metal so violently that they generate magnetic fields thousands of times stronger than Earth. These fields don't just funnel particles, they whip them, accelerating charged material to near light speeds before slamming it into the atmosphere. The result: auroras that don't dance, they rage, igniting chemical reactions in the upper air that paint the sky in hues we don't even have names for. Yet there's a twist: the lights aren't uniform. While Earth's auroras cluster near the poles, this planet's engulf everything from equator to poles in a ceaseless wildfire of photons. That suggests something stranger than mere magnetism at work, perhaps an external energy source. Some astronomers point to the planet's turbulent relationship with its twin, a nearby neutron star whose spinning magnetic field lashes the planet's atmosphere like a cosmic bullwhip, injecting it with enough energy to keep the auroras burning. Others speculate the planet plows through clouds of antimatter drifting in the void, the annihilation of particles sparking cascades of light. Then there's the color palette. Typical auroras glow green from oxygen or red from nitrogen, but the Aurora planet's spectrum includes impossible shades. A searing metallic gold, a deep ultraviolet that registers only on instruments, and a fleeting starlight blue that seems to pulse in sync with distant cosmic events. These anomalies hint at atmospheric chemistry beyond our periodic table, or even quantum effects where the planet's magnetic field twists particles into exotic states before they decay. But the most haunting detail the auroras learn: over decades of observation, astronomers noticed the light patterns adapting, avoiding certain regions after meteor strikes, or intensifying over newly formed volcanic plains as if drawn to the heat. It's as if the planet's magnetic field isn't just a force but a system, responding to its environment with eerie precision. Whether it's a natural feedback loop or something far stranger, one thing's clear: in NGC 262, even the weather knows how to put on a show that defies the universe's rules. The Whispering Comet glides through NGC 262 like a cosmic eavesdropper, its icy tail painting streaks of frost across the void. At first glance, it seems ordinary, a frozen relic from the solar system's infancy. But tune a radio telescope to its frequency and the illusion shatters. Instead of the usual static or predictable solar bursts, the comet crackles with something unnervingly familiar: patterns that mirror human speech. Not words, not languages, but the cadence and rhythm of conversation, rising tones like questions, clipped bursts like exclamations, even pauses that feel deliberate. It's as if the void itself has learned to whisper. So where does this eerie soundtrack come from? The leading theory points to plasma vibrations. As the comet nears stars, solar radiation boils ice into charged gas, creating a turbulent sheath of ionized particles around it. Under the right conditions, these particles can oscillate in ways that produce radio waves, much like lightning generates static on Earth. But instead of random noise, the comet's plasma might be shaped by its unusually lopsided magnetic field, twisting emissions into peaks and valleys that mimic speech rhythms. Think of it as a celestial violin. It strings the magnetic field lines vibrating as solar winds bow across them. Yet there's a glaring hole in this explanation: the patterns evolve. Natural plasma noise should be chaotic, but the whispering comet's signals shift in cycles, repeating certain sequences before introducing new ones, almost like a language learning new syntax. Some astronomers argue this could be resonance, a feedback loop where the comet's own emissions bounce off nearby cosmic dust, creating echoes that reinforce specific frequencies. Others point to the comet's bizarre composition. Scans reveal veins of metallic hydrogen threading its core, a substance so rare it might vibrate at frequencies that structure the radio noise into something eerily coherent. Then there's the far wilder possibility that the signals aren't natural at all. The comet's most infamous broadcast, dubbed the Laughing Pulse, consisted of rapid, staccato bursts that, when sped up, uncannily resembled human chuckling. Skeptics dismiss it as pareidolia, our brains hardwired to find meaning in randomness, like seeing faces in clouds. But a fringe group of researchers insists the patterns are too intricate to be accidental. Could the comet be a relay, its icy body laced with some ancient technology designed to amplify or repeat signals? Or worse, is it a lure broadcasting faux familiarity to draw attention? The truth might lie somewhere in between. In 2018, a probe's close flyby detected minuscule structures in the comet's crust, microscopic tunnels too regular to be cracks, yet too small to be artificial. One hypothesis suggests these could be cryovolcanic vents, spewing pressurized gas that modulates the radio emissions like a cosmic flute. Another proposes quantum vibrations in the comet's exotic ices, their atomic lattice vibrating in ways that structure the noise. Whatever the source, the whispering comet forces us to confront a discomforting idea. The line between coincidence and communication might be thinner than we think. In a universe where pulsars keep perfect time and black holes sing, why shouldn't a comet learn to whisper? Whether it's plasma physics, cosmic archaeology, or something beyond our grasp, one thing's clear: NGC 262 has a way of turning even the quietest objects into voices. And sometimes the most haunting questions aren't about what's being said, but why we're so desperate to hear meaning in the static. Among the endless wonders of NGC 262, few sights defy expectations quite like the metallic ocean, a planet where the very concept of land gets rewritten. Imagine standing on its shoreline, if such a thing exists, watching as vast silver waves roll under a bruised violet sky. But these aren't water waves, they're liquid metal, churning at temperatures that would vaporize steel, their surfaces reflecting distant starlight like a funhouse mirror. This isn't just molten rock, it's an entire world where the crust dissolved long ago, leaving behind a seething, mercury-colored expanse stretching unbroken to the horizon. How does a planet become a literal forge? The answer lies in a perfect, or perhaps perfectly catastrophic, storm of conditions. Most terrestrial planets cool over time, their molten cores solidifying into rigid mantles. But the metallic ocean's core is a radioactive powerhouse, rich in unstable isotopes like uranium-235 and thorium-232, whose decay generates relentless heat. Combine that with tidal flexing from a nearby neutron star kneading the planet like dough, and you've got a recipe for perpetual liquefaction. The result: a surface that never cools, where metallic elements stay suspended in a shimmering, conductive soup. What's truly bizarre, though, is what floats on that soup. Scattered across the ocean are islands of solidified alloys, not rock, but impossible metallic compounds forged in the planet's extreme pressures. Some contain crystalline structures seen only in lab-created superconductors. others drip with iridium gold mixes that defy natural solubility rules. These aren't just geological oddities, they're windows into material science's future. Researchers speculate the planet could be a cosmic workshop where pressures and temperatures we can't replicate on Earth craft substances with revolutionary properties. Room temperature superconductors, unbreakable space-age ceramics, or even metals that remember their shape after extreme deformation. Then there's the motion. Earth's oceans follow predictable currents driven by wind and rotation. The metallic ocean obeys different laws. Its flows pulse in fractal patterns as if guided by invisible magnetic scripts. Probes have detected waves moving against the planet's spin, their crests glowing with eerie bioluminescence caused by charged particles exciting exotic vapors. Some researchers believe the ocean itself might be a colossal dynamo, generating electromagnetic fields so complex they resemble neural networks. Could there be a form of weather here beyond anything we understand, storms that aren't just turbulence but self-organizing magnetic intelligence? The most haunting question, though, is whether this ocean is alive, not in the biological sense but as a system. Certain metallic compounds, when suspended in this environment, exhibit behaviors eerily reminiscent of proto-metabolism, self-assembling into temporary structures, exchanging electrons in chain reactions that resemble respiration. It's a stretch to call it life, but in a galaxy where dust clouds mimic intelligence and black holes sing, why couldn't a planet evolve its own kind of pulsating metallic vitality? Whether it's a cosmic smithy, a laboratory for alien physics, or something beyond our current science, the metallic ocean shatters every assumption about what a planet can be. It's a reminder that the universe doesn't just create worlds, it engineers them with a creativity that humbles even our wildest imaginations. And if liquid metal can dance under an alien sky, what other marvels hide in the dark, waiting to rewrite the rules? Orbiting a lonely star in the outer reaches of NGC 262, the Dyson sphere fragment hangs like a shattered crown, a curved slab of impossibly smooth material stretching thousands of miles across, its edges glowing faintly with captured starlight. This isn't just space debris, it's a cosmic puzzle piece, something too massive and too precise to be a random formation. Most asteroids and wreckage tumble chaotically, but this fragment maintains a perfect geosynchronous orbit, as if locked in place by invisible hands. Its surface is a patchwork of geometric panels, some still shimmering with a glass-like sheen despite eons of exposure to cosmic radiation, while others hang in tatters, revealing intricate honeycomb substructures beneath. The idea of a Dyson sphere, a megastructure built around a star to harness its energy, has been speculative science fiction for decades. But standing in the shadow of this fragment, fiction starts to feel uncomfortably plausible. The composition alone defies natural explanations. Spectroscopic scans reveal alloys with atomic arrangements not found in nature, metals forged at temperatures and pressures achievable only in labs or perhaps advanced industrial facilities. Even more telling are the energy signatures, residual thermal patterns that suggest the fragment once channeled stellar energy on an unimaginable scale, like a cosmic power grid now fallen dark. Could this be natural? Some astronomers argue for a freak stellar event, a supernova's shockwave compressing nearby matter into a crystalline lattice, or a neutron star's magnetic field sculpting debris into temporary order. Others point to theoretical stellar pearls, rare formations where a star's own plasma cools into strange metallic structures under extreme conditions. But these theories struggle to explain the fragment's intentional seeming geometry. The panels aren't just orderly, they're modular, with repeating units that resemble circuit boards scaled up to planetary size. Natural processes don't create hexagonally tessellated plating or nested parabolic arrays unless, of course, we've underestimated nature's architectural flair. Then there's the orbit. The fragment doesn't just drift, it balances perfectly between the star's gravity and its own momentum, a dance that should degrade over time without adjustment. Yet it hasn't wavered in centuries of observation. That kind of stability hints at systems still functioning beneath the surface, maybe inertial dampeners, gyroscopic stabilizers, or something beyond our engineering vocabulary. A handful of faint, rhythmic radio pulses detected from the fragment's core only deepen the mystery. They're too weak to be a beacon, but too regular to be stellar interference. Maintenance signals a dying power source or just the creaks of an ancient structure cooling in the void. The most unsettling possibility is that the fragment isn't broken at all, it's waiting. If this is just one piece of a larger structure, where are the others? Were they destroyed in some cataclysm or deliberately detached? And if a civilization built this, why leave it behind? The optimists imagine a relic of a society that moved on to greater things, leaving their old tech to orbit forgotten. The pessimists whisper of warnings, a monument to ambition that outpaced wisdom. Whether it's alien engineering or nature's most elaborate coincidence, the Dyson sphere fragment forces us to confront a humbling truth. The universe builds on scales we're only beginning to glimpse. And in NGC 262, even the ruins refuse to be ordinary. Buried in the cosmic archives of NGC 262, there's a star that shouldn't exist, a celestial relic so ancient it threatens to rewrite the timeline of the universe itself. The paradox star glows with the quiet defiance of a pensioner who outlives their own birth certificate, its light carrying whispers of an age predating the cosmos as we know it. According to every reliable measurement, this star is older than the Big Bang's afterglow, a cosmic impossibility that leaves astronomers torn between awe and existential dread. How does a star outage the universe? The answer might lie in our own blind spots. At first glance, the paradox star's age comes from its composition, a nearly pristine mix of hydrogen and helium with only trace amounts of heavier elements. Stars like these, called population Roman III stars, are theorized to be the universe's firstborn, forged from the raw material of the Big Bang before supernova seeded space with metals. Yet even the earliest stars shouldn't predate the universe's 13.8 billion-year clock. The discrepancy sends scientists scrambling for explanations, from faulty stellar clocks to the unsettling possibility that our cosmic timeline is missing entire chapters. One leading theory blames redshift errors, a glitch in how we measure the star's light. As the universe expands, wavelengths stretch, shifting starlight toward the red end of the spectrum. By calculating this redshift, we estimate distances and, by extension, ages. But what if the paradox star's light got contaminated? Imagine it passed through an invisible cloud of primordial gas or got bent by a hidden gravitational lens, distorting its redshift into an illusion of antiquity. It's like mistaking a candle's reflection in a funhouse mirror for the real thing, a trick of cosmic optics rather than a true anomaly. Then there's the quantum fluke hypothesis. Certain models of the early universe suggest spacetime might have undergone false vacuum decay, where pockets of reality aged at different rates before stabilizing. If the paradox star formed in one of THESE Chinese letter pockets, it could genuinely be older than its surroundings, a relic from a proto-universe that flickered into being before ours. It's a fringe idea, but in a galaxy where black holes sing and dust clouds move with purpose, even the wildest theories deserve a hearing. But the most unsettling possibility: that our understanding of stellar aging is fundamentally flawed. Stars burn fuel at rates dictated by physics we thought we'd mastered: nuclear fusion, gravitational compression, radiative transfer. Yet the paradox star's energy output suggests it's somehow cheating, like a candle burning twice as long on half the wax. Could unknown quantum effects in its core slow its metabolism? Or is it feeding on something darker, perhaps vacuum energy, or even the fabric of spacetime itself? The implications are staggering. If the paradox star truly predates the universe, it could upend cosmology's bedrock principles, forcing us to reconsider the Big Bang singularity or entertain multiverse theories where time branches in ways we can't perceive. Even if it's just a measurement error, the fact that nature can mimic such a paradox is a humbling reminder. The universe is under no obligation to make sense to us. As telescopes continue to monitor this celestial elder, one thing becomes clear: NGC 262 doesn't just house mysteries, it architects them. And in the paradox star's flickering light, we're left to wonder, are we reading the universe's story correctly, or just a dog-eared page torn from a book we've yet to find? At the edge of NGC 262's spiraling arms, the Gateway Nebula stretches across the void like a cosmic hallway, a vast tunnel-like structure of glowing gas and dust that seems to beckon travelers toward its shadowed heart. Unlike most nebulae which sprawl in chaotic splendor, this one forms a near-perfect cylindrical passage, its walls sculpted by forces we don't yet understand. From a distance, it looks like a wormhole ripped straight from science fiction, its entrance wreathed in tendrils of ionized hydrogen that pulse with an eerie, rhythmic light. Step closer and the illusion only deepens. Starlight from the nebula's far side doesn't just pass through, it warps, bending around the tunnel's curve as if space itself has been folded. So is this a natural formation or something more? One camp of astronomers argues for an extreme stellar wind scenario. Picture a dying star, its final eruptions blowing away material in a focused jet, like a cosmic hose carving a path through surrounding gas. Over millennia, radiation from nearby stars could have ionized the tunnel's walls, making them glow while leaving the central path dark. It's a rare but plausible phenomenon, nature's version of a laser cutting through smoke. Yet there's a problem with this theory: the tunnel's geometry. Natural jets tend to be messy, flaring at the ends or kinking under magnetic pressures. The Gateway Nebula's passage is unnervingly straight, its edges sharp as if drawn with a ruler. Even stranger, the nebula's interior exhibits gravitational anomalies, patches where the pull of invisible mass seems to twist light into knots. Some researchers speculate these could be topological defects, wrinkles in space-time left over from the universe's birth where the laws of physics briefly glitched. If true, passing through the tunnel might not just be a journey through space, but a dip into deeper layers of reality itself. Then there's the light inside. Most nebulae scatter starlight into soft halos, but the Gateway's tunnel acts like a fiber optic cable, channeling light along its length with minimal distortion. Stars viewed through it don't twinkle, they stretch into luminous threads, their images smeared as if seen through flowing water. This effect has led a handful of theorists to propose an even wilder idea. The nebula might be a stabilized wormhole, its structure artificially reinforced by some long-gone civilization. While there's zero direct evidence, the precision of the tunnel's light-bending properties fuels speculation. After all, in a galaxy where black holes sing and dust clouds mimic intelligence, why couldn't a nebula be engineered? But the most haunting detail is the nebula's silence. Radio telescopes aimed at its heart pick up nothing: no static from ionized gas, no whispers of distant stars. It's as if the tunnel absorbs sound waves the way its walls bend light, creating a pocket of perfect quiet. That absence has inspired some to nickname it the Cosmic Library, a place where the universe's secrets might be stored if only we could hear them. Whether it's a sculpted stellar grave, a space-time shortcut, or something beyond our current physics, the Gateway Nebula does more than fascinate, it invites. It's a reminder that the universe builds doors where we least expect them, and that some mysteries aren't meant to be solved from the outside. From the Twisted Nebula's writhing tendrils to the paradox star's ancient glow, NGC 262 has taken us on a tour of cosmic absurdity, a gallery of celestial oddities where the universe seems to toss the rulebook out the airlock. Each of these 30 objects defies expectations in ways that leave even seasoned astronomers speechless. The phantom star's disappearing act mocks our understanding of stellar life cycles, while the gravity anomaly warps spacetime like a funhouse mirror. The diamond planet dazzles with its impossible geology, and the screaming black hole serenades the void with gravitational waves turned sound. Then there's the living dust cloud pulsing with eerie synchrony, and the Clockwork pulsar ticking with precision that borders on artificial. Let's not forget the bioluminescent gas giant, painting its skies in colors we can't name, or the stealth galaxy, a shadow so complete it swallows light itself. What ties these enigmas together? More than just their strangeness, they're cosmic conversation starters, each one prying open cracks in our current theories. The lava waterfall's relentless flow challenges planetary cooling models, while the quantum quasar's fractured reality questions causality itself. The cosmic web's geometric perfection hints at hidden forces weaving the galaxy together, and the vanishing moon's cloak and dagger routine suggest celestial mechanics we've yet to grasp. Even the humble singing asteroid, with its metallic hum tuned to the universe's oldest frequencies, whispers that harmony might be written into the fabric of space. But here's the real kicker: NGC 262 isn't done surprising us. For every mystery we've uncovered, a dozen more lurk in the dark. Could the fractal nebula's repeating patterns hold a key to universal structure? Might the Dyson sphere fragment's eerie geometry rewrite our search for alien intelligence? And what of the Gateway Nebula's tunnel? Is it a natural marvel or a roadmap to realms beyond our own? The beauty of this galaxy lies in its refusal to conform, its way of turning every "that's impossible" into a "wait, look again, so now it's your turn." Which of these cosmic rebels captured your imagination? Was it the hexagonal storm's razor-shaped fury, or the frozen lightning's eternal snapshot of chaos? Drop your favorite in the comments, we're obsessively checking them. And if your brain craves more mysteries, hit subscribe. The universe is vast, unpredictable, and endlessly creative. NGC 262 is just one stop on the tour, ready for the next.